So in this class, I will present a generalized version of the vacuum energy or of the lambda term, which is often called quintessence, just to basically to generalize the result that we had so far. And I will also introduce an additional topic, the topic about the age of our universe, which in principle provides additional indications that we need something like a lambda term. And that's why it's a closely related topic. Now, now for our lambda term, as we've briefly seen, it's a term that corresponds to a negative pressure, where the pressure is equal to minus the energy density itself. Which is a very unusual term. And in principle, it can be somewhat better understood if we look at it in a more general way, if we parameterize the equation of state as P equal omega times C squared. In principle, that's a normal parameterization of the equation of state. If we adopt omega equals 0, this corresponds to pressureless matter. If omega is 1/3, then this corresponds to the radiation dominated epoch. While here in this investigation, we will focus on the case where omega lies between 0 and -1. And we want to understand now what are the implications of a negative pressure. From the first law, if we insert this definition for our pressure term, we obtain an equation that depends basically on the density and the scale factor, and we can make a separation of variables here, bringing all the terms that depend on the density to the left side and all that depend on the scale factor A to the right side. We can then, in principle, integrate this equation, and what we find is that the density should be proportional to a to the -3 multiplied with 1 plus omega. So we obtain a very general relation on how density evolves with the scale factor for a general equation of state. Now, we can recall some limiting cases here that we already know, like for the pressureless matter with omega equals 0. You see here the density scales as a to the -3. That's a result we already had before. And if we adopt here the equation of state for the cosmological constant, so if omega is equal to -1, then the density here will be constant. So then we have a true constant energy density due to the vacuum. In addition, of course, there can be various cases in between if omega is somewhere in between 0 and -1. Now, to understand better the meaning of such a component, we can look at the acceleration equation and insert also here our equation of state. Then the right-hand side of this acceleration equation will become proportional to 1 plus 3 omega. And if you look at it, you can then see that to obtain a negative equation, a negative result here, so to obtain acceleration, you need to have a negative value for 1 plus 3 omega so that it compensates for the minus sign in front of the expression. So we need to have omega smaller than -1/3. It has to be more negative than this number. If the pressure is only slightly negative, it's basically not sufficient to drive an accelerated expansion of the universe. It has to be negative enough for an accelerated expansion. In principle, this result can be evaluated further. We can replace the rho Q using the relation on how the density evolves with the scale factor, and we can insert this equation directly in the acceleration equation and then evaluate the acceleration equation today. And this allows us to determine basically the deceleration parameter in the universe today, which is minus a double dot today divided by at0 divided by h0 squared. And if you do the calculation, then you find that it's 1/2 omega q 1 plus 3 omega. And from this, you basically see the same thing. To have acceleration today, to have acceleration, the q0 parameter has to be negative. So that means omega has to be smaller than minus 1/3. If it's not negative enough, then q0 will be positive. That means there will be deceleration. Now, from this general consideration, we come to something more specific, the age of the universe in the different models. And we will start with the matter-dominated universe, as it's the most intuitive one, even though we will see that the matter-dominated universe will not be consistent with simple observations of the age of our universe. So we've already shown that in the matter-dominated universe, the scale factor is given as the current time or age of the universe t divided by t0, the age of the universe today, to the power 2/3. We've also shown that the Hubble parameter h, or a dot over a, can be related to time as 2/3 t to the minus 1. If we solve this for the time or the age of the universe, and if we evaluate it today, then we can basically determine what the current age of the universe is, and we can evaluate it from the Hubble constant that we know. And if we do that, and if we evaluate it, we obtain a time t0 that is about 6.5 billion years, or, well, if we insert the correct value for the small h for the Hubble rate, then it's about 9.3 billion years, which, of course, on the one hand is a long time, but we also do have objects in our Milky Way galaxy that are considerably older. We have stars with an age of about 13 billion years. And of course, the universe has to be older than the oldest stars. That's why the matter-dominated universe cannot be the correct result. We can in principle do the same calculation for radiation-dominated universe. Here the scale factor A of t is proportional to t over t0 to the 1/2. And in this case, the Hubble parameter h is equal to 1/2 t to the minus 1. And which we can evaluate today, yielding h0 equal 1/2 t0, or t0 equal 2h to the h0 to the minus 1. Here the universe would be older, but we know it is not dominated by radiation today. It was only dominated by radiation for a very short time, about 100,000 years, so that's not sufficient. And that's why it doesn't help us in a direct way, but at least it shows that the age of the universe depends on the content of the universe. That's in a way useful, because then with a different content of the universe, we can maybe fix the age of the universe as well. Now, for the cosmological constant, we've derived a solution. We've seen that the scale factor is an exponential function of plus minus square root lambda over 3 multiplied with the time. For the expanding universe, we need a plus sign. But in general, for an exponential function, at any finite time, this function will always be positive. So the scale factor here was always positive. This means here at each finite time the universe has existed and the scale factor was finite, there was no Big Bang in this model. That's a very significant change compared to the matter-dominated universe and the radiation dominated universe. Now our universe, it does not only consist of lambda, it only consists of matter, and in the past the matter was the dominant component, the lambda only became important more recently. That's why in the real universe there was still a Big Bang, because in the past the matter was more important than the lambda. But nevertheless, the lambda can help us also in our universe to increase the age of the universe. And indeed, there is a formula which is based on a long derivation, but it's given here in equation 78, where you see for a universe consisting of non-relativistic matter and lambda, how you can calculate the matter, the current age of the universe. This assumes also that the geometry of the universe is flat, so the sum of omega lambda plus omega matter is equal to 1. And if we insert here approximately the parameters of our universe today, then we find an age of about 14 billion years, which is about fine and consistent with the measurements of the oldest objects in the universe. Now, to give you some examples of age determinations, our sun has been compared with very detailed stellar evolution models, which show that it must be about 5 billion years old. This is also consistent with age determinations of meteorites or with material on Earth, which all points at a very similar age, that also the Earth formed at a time that was similar. There are, of course, much older objects in our Milky Way, like the oldest globular clusters in the Milky Way. They have an age of about 12 to 13 billion years. The oldest stars have an age of about 13 billion years, and that is incompatible with a matter-dominated universe. There have been very accurate measurements of the cosmological parameters with Planck, which give an age of about 13.8 billion years. That's about the best age we have at the moment. One can do additional estimates also using nuclear reactions based on material in our galaxy. Sometimes this is done with the uranium isotopes, the isotopes U-235 and U-238. Their ratio at the time of production through nuclear reactions is known. That's known from nuclear physics, and it's about 1.65. These isotopes are unstable. They go through radioactive decay with an exponential decay law proportional to the exponential of minus lambda t, but they have different decay rates lambda for each isotopes. These decay rates have been measured in the laboratory. They are given here, and they're different by a bit roughly a factor of 5, let's say. And based on this difference, one can predict how the ratio of these isotopes should depend over time. We just need to multiply the initial ratio 1.65 with the quotient of these exponential expressions. And if we compare how this evolves over time with the present ratio that is known from observational data, this ratio has decreased considerably. It's now 0.0072. Then we can solve for the time, and we determine a time of about 6.6 billion years. Now this time may not seem as huge as other times before, but the important thing is, the age that we derived here is not the age starting from time 0. This is the age when all the uranium isotopes had already been produced. So when all the heavy elements had already been in place, when they were ejected from supernovae after a lot of stellar nucleosynthesis and after the accumulation of the Milky Way galaxy. So all of this came before. All these elements had to be produced, and only then the radioactive decay started. So in addition, the total time to do all this would be even much, much longer. And that's why it's another important reason, yeah, to have additional time available and to be consistent with our age determinations within the cosmological model. Of course, here this is an approximate argument. To understand this better, one has to look at cosmological simulations of galaxy formation to see how much time it takes to build up a certain amount of stellar mass. Nevertheless, this is in principle, yeah, to give you some idea about the methods that are available, which in principle point towards, yeah, ages of the universe that either require or are in favor of having lambda, yeah, which together with other observations that we will still get to know, yeah, provide a consistent indication that lambda is an important component of our universe.